So building on the concepts of stoichiometry and limiting reagent, let's talk about percent yield problems, because it's basically a step up from those and the final step up on the topic. And as always, a percentage is just the part over the whole times 100. So how are we defining our percentage this time? Well, for percent yield, the percentage is going to be the actual experimental yield divided by our calculated theoretical yield times 100 as always. So we've got to find the theoretical yield via stoichiometry and also check for limiting reagents. So we might have to do the calculation twice to get theoretical yield. Actual yield is usually a given, although we can give all parts of the equation but one and ask you to calculate it. However, the usual method, especially in lab, is to measure your actual yield that's given to you, then calculate the theoretical yield and calculate your percent yield. So let's do an example. For the following balanced equation, 0.504 grams of hydrogen gas is produced. What is the percent yield if 4 grams of sodium metal and 13 grams of water are reacted to form hydrogen gas and sodium hydroxide? So this is a single replacement reaction. It's already balanced. If it weren't balanced, we'd have to balance it immediately. That's what we do with stoichiometry problems. And we immediately diagram the reaction for mass, the number of moles corresponding to the given masses experimentally, and then we calculate the molar mass from the periodic table. So what is given can already be put in. We have 4 grams of sodium metal and we have 13 grams of water, and we must calculate the theoretical yield of hydrogen gas to compare it to the actual yield of hydrogen gas. Okay, and so we also have to calculate the molar masses from the periodic table. I've done that ahead of time. We don't care about sodium hydroxide because it's not involved in the problem. So what do we have to do? Well, we can never compare grams to grams, so we've got to convert to moles and then use the mole ratio from the balanced equation to convert to moles of hydrogen gas, and then eventually to grams of hydrogen gas. Okay, and because we're given 2 sets of information, we also have to calculate what the theoretical yield would be if H2O is our limiting reagent. Okay, so we're going to have to do this process twice because we're in a limiting reagent situation where we do not know what the limiting reagent is. Okay, and so let's do things one step at a time and find what the theoretical yield is if sodium is limiting. Okay, and so we say, what's the given? Well, it's 4 grams of sodium metal. We want to get rid of sodium metal. Let's try to draw a straight line. So we cancel it out on the bottom. We want to go to moles of sodium metal. Grams to mole is the molar mass, so 22.99 grams per 1 mole. Cancel the grams of sodium. Now we want to get rid of moles of sodium and get moles of hydrogen gas. And the balanced equation says 1 mole of hydrogen gas, 2 moles of sodium from the coefficients of the balanced equation. Now we're rid of sodium. We want moles of hydrogen to go away. And we want to get grams. We can compare grams of one substance to moles of that same substance. That's the molar mass. And so 2.016 for 1 mole. Okay, and we can calculate what the theoretical yield is if sodium is limiting. And we get 0.1754 to 3 significant figures, 5 grams of H2. as our theoretical yield. Okay, but we also have to check for what if water is the limiting reagent. And so we've got to go through the roadmap again and solve again. Okay, and so if water, we start with 13 grams we want to get rid of water and get moles. That's the molar mass, so 18.02. Want to get rid of moles of water and get moles of H2. That's coefficients of the balanced equation, so 1 for H2, 2 for water, again same mole ratio by coincidence. Grams, grams, moles, moles. We want to get rid of moles of H2 and get grams of H2 from the theoretical yield. And what do we have? Well, grams of H2, molar mass is 2.016, just like before, per 1 mole. And let's see what our theoretical yield is. And I get 0.727 grams of H2 to 3 significant figures. So 0.727 is larger than 0.0175. So sodium is the limiting reagent. That means the theoretical yield is 0.175. And so if we finish the problem and calculate our percent yield, we want actual yield, which is 0.504, divided by the theoretical yield, 0.175 grams. Percentage is unitless, 0.504 divided by 0.175, and we get, times 100, 288% yield, which, if we're paying attention, is impossible. So we have to acknowledge that there's a problem with the experiment. Okay, we can't get more yield than is possible. 100% is maximum, and it's really unobtainable. Okay, so getting a perfect reaction, every atom out that you put in, is very difficult to do. And so we've got to be able to recognize that when we get a percent yield greater than 100, that means we have a big problem with the experiment, either error on our part or an inconsistent premise based on the experiment. So be careful about these in lab. Most problems give you a percentage under 100%, however, for the problems, but they don't have to. And remember, whenever that happens, it's a problem with the experiment.